Section 3.7 Optimization Problems, Example 1. A rectangle is bounded by the x and y axes, and the graph of y equals the quantity 6 minus x divided by 2. What length and width should the rectangle have so that the area is a maximum? In order for us to figure this out, I would graph this so that we can get a visual picture of what's going on. So I'm going to draw a graph. Here's my x and y axis. Now, the equation y equals the quantity of 6 minus x over 2 is actually a line. So I'm going to rewrite that in a linear format so that we recognize that this is negative 1/2 x plus 3, which means that our line has a y-intercept of 3 and a slope of negative 1/2. So we actually have a line that is going to have a y-intercept at 3 and x-intercept at 6. This is the line that we are talking about. So what we're going to do is we're going to create a rectangle inside this triangular shape, and we are going to figure out what dimensions that rectangle needs to have in order to get the most area. So since we are trying to maximize the area, what I would start with is the area of a rectangle. Now, the area of a rectangle is typically the length times the width. However, in this case, the length is going to be x, and the width of it, or the height of it, is going to be y. So I'm going to transfer my formula to be in terms of x's and y's. So a is equal to x times y. Now, at this time, we have two independent variables in there. We have the x and the y. So what we want to do is we want to take a secondary equation, in other words, an equation that is not going to be optimized, and we want to substitute it in. Since the area is the equation we want to maximize, I'm going to leave that one alone. But I can come up here to the equation of my line, and I can substitute that into the variable y. So the area is going to equal x times negative 1/2 x plus 3. This allows me to find the area, but in terms of a single independent variable instead of two of them. Now, since we're going to need to find a maximum, that means we're going to have to take the derivative. So I'm going to clean this equation up to make it as easy as possible to take the derivative. So if I distribute the x, we have negative 1/2 x squared plus 3x. Now, before we take the derivative, let's talk about what the domain is. I understand that this equation right here technically has no domain restrictions. However, we're talking about the x representing how wide or how long the side of the rectangle can be. So we are limited to how long it can be by being inside this triangle. So the domain of x is going to have to be somewhere between 0 and 6. So when we talk about what the feasible domain is, we cannot have anything outside of 0 and 6. Now, let's go ahead and take the derivative. So a prime is equal to negative x plus 3. We know that we set this equal to 0 to find our critical values, and our critical value will be x equals 3. So, testing this just to make sure that it truly is a maximum, we have our endpoints of 0 and 6. 3 is in the middle, and we're going to test these in our derivative. If I plug in something between 0 and 3, like a positive 1, we end up getting a positive. If I plug in something between 3 and 6, like a 4, we get a negative. Since the derivative changes from positive to negative, that means the area is going to change from increasing to decreasing, which means that this 3 is going to be a relative max, which is what we were looking for. Now, the directions say what length and width should this rectangle have. So we now know that the x-coordinate is going to be 3, and we need to find the y-coordinate that goes with it. The easiest place to figure out the y-coordinate that's going to go with it is actually right back up here in our secondary equation. If I take the 3 for x, plug it in, and evaluate, we end up getting the y value is 3/2. So the maximum area is going to occur when the rectangle has a length of 3, so it's actually going to be here, and a height of 1/2. So here is the rectangle that we're talking about.